So my lecture will be about some developments, maybe not necessarily so recent, but some developments in the Langlands program. So I want to start with just a few words about the Langlands program. So it's sort of meant to be a grand unified theory of mathematics that connects number theory to other areas, such as representation theory, harmonic analysis, and algebraic geometry. And it's related, at least in its number theoretic incarnation, it's related to some of the oldest and deepest questions in number theory. And in particular, the notion of Langlands reciprocity goes back to Gauss's law of quadratic reciprocity. So let me start there. This is something that's related to a basic question you can ask about whole numbers, which is what can be the last digits of perfect squares? And in particular, you can ask about the last digits of perfect squares in base given by any prime number. So if P and L are two different odd primes, then the law of quadratic reciprocity relates whether P can be the last digit of a perfect square in base L, by which we mean that it's a quadratic residue modulo L, to whether L is a quadratic residue modulo P. And the precise relationship is this one. And so here, if I'm going to take P to be equal to 3, then you see on one hand, this side depends on L modulo 4, and this will depend on L modulo P. So all in all, the number of solutions to the congruence x squared minus 3 equals 0 modulo L only depends on L modulo 3 times 4, so on L modulo 12. In other words, you can read this off the 12-hour clock. It just depends on where L falls on the 12-hour clock. And the number of solutions can be predicted in a more sophisticated phrasing by saying that it's encoded in a Dirichlet character, which is this finite order character of Z mod 12Z cross. Now, this is the very first instance of a reciprocity law. And you can ask about generalizing this by looking at equations that are maybe higher order equations, or maybe in more than one variable. And you can ask about counting the number of solutions of such equations modulo primes and seeing if there is a way to generate the number of solutions. So there's a higher dimensional reciprocity law that can sort of allow you to do this. Of course, the notion of reciprocity is, you have to kind of be a little bit less precise than in the one-dimensional setting, but in the higher dimensional setting, you can still do something like this. So you can look at the following power series, which is obtained by this infinite product. So you expand it out in a power series in the variable q, and then I claim that it knows something about the cubic Diophantine equation, y squared plus y equals x cubed minus x squared. Right, so why would that be? Well, I want to kind of argue this by looking at precise values. So let's say that we look at the coefficient of q to the L in the expansion of f of q. As L runs over almost all prime numbers, I'm just going to skip 11 for technical reasons. And you can look at the number of solutions to the cubic equation, y squared plus y equals x cubed minus x squared, but we want to think of it as a congruence. So we want to look at the number of solutions modulo L. And again, we let L run over almost all primes, we just skip 11. So we get these two tables of values. And it turns out there is a close relationship between these values. I'm not sure if, maybe if you see this for the first time, it's not obvious to you. But let's look here. For instance, here you have 19, and over here you have 4. They add up to 13. Here you have 24 and minus 1. They add up to 23. 29 and 0 add up to 29. So it turns out this just persists no matter how large L gets. You always get AL is equal to L minus NL. So the coefficient of Q in this expansion knows about this sort of error term, which is the difference between the prime and the number of solutions to the equation. So this isn't quite as clean as in the quadratic reciprocity setting, but it's still a way to generate the solutions. So it turns out that there's a reason, a very deep reason for this relationship. The power series f of q is really the Fourier expansion of a modular form. And the Diophantine equation E represents an elliptic curve over q. So a modular form is a holomorphic function on the upper half plane that has a lot of symmetries. And it's really an object that lives in the world of harmonic analysis. An elliptic curve is a smooth projective curve of genus 1. And then if we take a rational one, so one whose equation is defined over q, then this is an object that lives in the world of arithmetic algebraic geometry. And this explicit reciprocity law that says that AL is L minus NL, this is really a consequence of the modularity of elliptic curves over Q, which played the crucial role in the proof of Fermat's last theorem. So what we've just seen has been an instance of the Langlands correspondence. So I want to talk about the Langlands correspondence from a slightly more general perspective in order to discuss some very recent developments. So the global Langlands correspondence is supposed to match spectral data, by which I mean systems of eigenvalues that you extract from the topology of certain highly symmetric spaces. And this is the kind of data that you see on the automorphic side. And this is like the sequence of coefficients of this power series in Q that we've seen. And it matches this kind of data with arithmetic data that you get by counting solutions to polynomial equations with rational coefficients. So this is the kind of data that you get, for instance, from this cubic Diophantine equation. And of course, that there are really infinitely many instances of the Langlands correspondence. And so in order to describe a particular one, you have to choose your setting, by which I mean you have to choose a global field, for instance, the rational numbers, or an extension such as a real quadratic field, Q adjoint square root 3, or an imaginary quadratic field, Q adjoint I, and a connected reductive group, which is, for instance, GLN, the group of n by n matrices, or SLN, invertible n by n matrices, or SLN, n by n matrices with determinant 1, or SP2n, which are 2n by 2n matrices that preserve the standard symplectic form. And so for the purposes of this talk, you can pretty much imagine that you're working with GLN or even just GL2. And hopefully this will have some meaning, even in this case. So there are two sides to the global Langlands correspondence. There's the Galois side and the automorphic side. And the Galois side is sort of easier. If you're coming to this from the outside, it's sort of easier to get a sense for it. So I'll start with that. So given a number field, we're interested in its absolute Galois group, which is the sort of inverse limit of the Galois groups of all the finite Galois extensions of your field. So this will see the automorphisms. For instance, if F is Q, this will see all the symmetries of algebraic numbers. And it's quite a complicated group. It's equipped with this profinite topology that turns it into a Cantor set. And it's very hard to study directly. So what we do instead is we try to understand this group by studying its representations, more precisely its continuous finite dimensional representations. And so a source of representations is comes from algebraic or arithmetic geometry, really. So for instance, if you take an elliptic curve over Q, then this elliptic curve also has a group law that is defined over Q. And so you can make sense of p to the n torsion points and the coordinates of those torsion points, the x and the y, when you solve the corresponding equation, are going to be algebraic numbers. And so you can view your p to the n torsion points. On one hand, you can view it as z mod p to the n z squared by thinking about what the p to the n torsion points on a torus, a one-dimensional torus look like. On the other hand, they're also equipped with an action of the absolute Galois group of Q, which comes from the fact that really the coordinates of these points are algebraic numbers. And as n varies, you can put these together into a system that gives rise to a Galois representation, a two-dimensional representation of the absolute Galois group of Q that is valued in GL2 of QP, where here QP is the field of p-adic numbers. So this is the p-adic completion of Q that you get by saying that two rational numbers are close if they are congruent modulo high power of P. And more generally, there is a machinery that is called étale cohomology, and the étale cohomology of algebraic varieties gives rise to, of algebraic varieties defined over number fields, gives rise to Galois representations. So you don't really need to know that you have a group law. That's just something that is convenient in order to give this sort of first example. But whenever you have an algebraic variety that's say cut out by some polynomial equations with coefficients in a number field, you can consider its étale cohomology, and that gives rise to a Galois representation. Okay, so on the automorphic side, you have some objects that at first appear more mysterious. And so an example of an object on the automorphic side, in the case that we're looking at, which is GL2 over Q, is a modular form. So this is a holomorphic function on the upper half plane that satisfies many symmetries and a growth condition. And I won't give you the precise formula, but I'll just say that the symmetries of the modular form are predicted by the action of SL2R on the upper half plane. So SL2R, the group of 2x2 matrices with determinant 1 and with real entries, acts on the upper half plane by this formula. And it's easy to check that if you start out with a complex number with strictly positive imaginary part, then you get a complex number with strictly positive imaginary part. And moreover, this action is transitive. And so you can really identify the upper half plane with the symmetric space for SL2 of R. It's the quotient of SL2 of R by the stabilizer of, say, the point I, which is SO2. All right, and just to give you an example, so a matrix that is in here is 1, 1, 0, 1, and this is going to send Z to Z plus 1. And so one thing is, if you have, so modular forms will actually be invariant under this particular transformation, and so they will be periodic with period 1. And this allows us to take their Fourier series. Now, modular curves are quotients of the upper half plane by congruent subgroups. So the symmetries are really under the action of the arithmetic group SL2Z or under the action of subgroups inside SL2Z that are cut out by congruence conditions. And so the point is somehow that you should think of the modular form as really living on the quotient of the upper half plane by the congruent subgroup. And here's a picture of a fundamental domain for the action of SL2Z on the upper half plane. So in order to construct the quotient, you need to identify that side, and this one, and this one. And so you get something that looks like a punctured Riemann sphere, possibly with some orbifold points. Now, for a smaller congruent subgroup, you need to take finitely many copies of this fundamental domain. And so ultimately the covering space would be different. So the quotient might look like a Riemann surface of higher genus, maybe something like this. So it's non-compact and has some genus. But one thing that happens in this case is that you have a complex structure on the upper half plane, and it turns out this descends to these quotients. And so these quotients really are Riemann surfaces. And something that's really miraculous in the theory is that these quotients arise from algebraic curves that are defined over number fields. And these are the so-called modular curves. And so because of this, you can consider the algebraic curves the corresponding algebraic curve, which is the modular curve, and take its étale cohomology, and that is a source of Galois representations. And so this allows you to start out with a modular form, but really view it as some kind of differential form on one of these quotients, then view it as contributing to the de Rham or maybe then singular cohomology of the modular curve, and then compare with the étale cohomology and find the Galois representation in there. Of course, to trace through all of this, you need to have some way of remembering your modular form. And the way that you do this is by means of some Hecke operators, which are some kind of averaging operators. And it turns out the modular forms that we're looking at are always going to be eigenvectors, simultaneous eigenvectors for all the Hecke operators. And so this is the part where you're keeping track of the spectral data. And turns out the Fourier coefficients that we were looking at, in fact, have an even deeper meaning as eigenvalues for Hecke operators. Okay, so let's go back to our example. So now I really want to take Q to be e to the 2 pi I z, and then this power series or infinite product in Q that we had in the beginning really has the meaning as the Fourier expansion of, well, some periodic function on the upper half plane. It turns out this is the Fourier expansion of a modular form. And we have our elliptic curve here. So when we say that E and F are matched under the global Langlands correspondence, what we mean is that there is an isomorphism between the associated Galois representations. This is the representation that you get by looking at the p to the n torsion points on the elliptic curve. And this is the representation that you cut out from the étale cohomology of modular curves. And the explicit reciprocity law that we saw sort of from the data can be recovered by taking this isomorphism of Galois representations and evaluating it at certain distinguished conjugacy classes that are indexed by these primes. L goes over all rational primes except for 11. It turns out that these conjugacy classes will give you well-defined elements up to conjugacy, and so the trace of the matrix is a well-defined number. Okay, so this is an instance of the global Langlands correspondence for GL2 over Q. And I guess the takeaway is that it's really mediated by these Galois representations, and it's really convenient to have this algebraic structure on the quotients of the upper half plane, which allows you to consider their étale cohomology and find the Galois representation that way. So the point of my talk is to discuss some developments in the past 10 years that are about going beyond this setting where you have an algebraic structure on your locally symmetric spaces, and so you have a direct connection to Galois representations. And sort of what you want to do is change your setting. So we were doing GL2 over Q or maybe SL2 over Q. And one way to change it is to replace Q by some finite extension. And so for instance, you could take a real quadratic field. It turns out that behaves very similarly to the original setting where you're working over Q. And another thing you can do is you can work with an imaginary quadratic field, such as the Gaussian numbers Q adjoined I. And it turns out this setting is fundamentally different. So if you take an imaginary quadratic field, then the associated symmetric space, so really it would be the symmetric space, I guess, for SL2 of C. This is going to be hyperbolic 3 space. So it's given by this formula, SL2C mod SU2. That's the maximal compact inside of it. And you can check that this has odd real dimension and has real dimension 3. So it turns out this can be identified with hyperbolic 3 space. And for a sufficiently small congruent subgroup inside SL2 of the ring of integers of OF, you can consider locally symmetric spaces, which are quotients of hyperbolic 3 space by these arithmetic groups. And the quotients are called arithmetic hyperbolic 3 manifolds, and they don't have the structure of algebraic varieties because they have real dimension 3. So they don't even have a complex structure. So the general case, if you want to do GLN over a number field, then this is going to typically behave like this case. You get some locally symmetric spaces that are smooth Riemannian manifolds, but that don't have necessarily more structure than that. So if F is a CM field, by which I mean like maybe something like a totally real field, but also an imaginary quadratic extension of a totally real field, then it turns out that you can still understand something about the associated locally symmetric spaces, so the case of GLN over F. And so this will include also the arithmetic hyperbolic 3 manifolds that we saw on the last slide. There was a theorem proved by Schulze in 2013 that looks at the singular cohomology of these locally symmetric spaces, even with torsion coefficients, and shows that there is a way to attach to systems of Hecke eigenvalues that occur in there, Galois representations. And this strengthens work of Harris, Land, Taylor, and Thorne that was completed actually in 2012, that do the same thing for cohomology with characteristic 0 coefficients. Cohomology with characteristic 0 coefficients really you should think of as automorphic forms. The generalization of the notion of modular form to this higher rank setting. However, yeah, I guess for cohomology with mod L coefficients, the best way to think about it is as giving you some mod L notion of an automorphic form. And the need to consider torsion classes comes from the Caligari-Garrity method. So in 2011, Caligari and Garrity proposed an extension of the Taylor-Wiles method to the setting of GLN over a number field. The Taylor-Wiles method that was so successful in proving modularity lifting theorems for GL2 over Q, and then also for some definite unitary groups, depends on a particular numerical criterion that just breaks down when you go to GLN over a general number field. And the breakdown of the criterion is also sort of, in some sense, related to, or seems to happen at the same time as when your locally symmetric spaces don't have an algebraic structure. And so Caligari and Garrity found a way to get around this. But what they did somehow required you to understand the cohomology of these locally symmetric spaces, and not just with torsion coefficients, but really not just with characteristic 0 coefficients, but really with torsion coefficients. Right. So I want to talk about another development that now is 2018, which is in the other direction. And really, I want to talk about consequences before I tell you some specific theorems. So one consequence will be on the Sato-Tate conjecture. So once you have the direction from Hecke eigenvalues to Galois representations, then you can ask about the other direction. And it turns out the other direction can be useful for proving results such as the Sato-Tate conjecture. So let's take the recall our elliptic curve, y squared plus y equals x cubed minus x squared. And remember that these error terms were important to us. So by a result of Hasse, these normalized error terms are actually in the interval -1, 1. And the Sato-Tate conjecture predicts that these numbers, as L varies over all primes, these numbers become equidistributed with respect to a natural probability measure, which is the semicircle probability measure. And here's a picture of a Sato-Tate distribution, maybe for a different elliptic curve, but that shows you how, like once you're really taking a large number of values of L, you get something that looks more and more like a semicircle. So for most elliptic curves over Q, the Sato-Tate conjecture was proved by Clauzel, Harris, Shepard, Barron, and Taylor in 2008. And the few remaining cases were solved maybe just a couple of years afterwards. Now, for elliptic curves over CM fields, such as, say, imaginary quadratic fields, we were able to obtain this result in 2018. And this is as a result of a large collaboration. So it's joint work with Patrick Allen, Frank Caligari, Toby G., David Helm, Bao Lehong, James Newton, Peter Schulze, Richard Taylor, and Jack Thorne. So you start with a CM field, and you look at an elliptic curve over that CM field that doesn't have complex multiplication. That's sort of the general case. Have an elliptic curve having complex multiplication is a special condition. And that case is well understood anyway. The general case, so then we were able to show that the elliptic curve is potentially automorphic and satisfies the Sato-Tate conjecture. And the way that we were able to prove this theorem is by looking at the elliptic curve and its symmetric powers and establishing a potential automorphy result for the associated Galois representations. So potentially automorphic here means sort of comes from an automorphic representation if you allow yourself to extend your base field from the original CM field F to some other extension. That is also going to be CM, but it's going to be larger, and so you possibly forget a lot. Maybe one comment to make is that the potential automorphy of elliptic curves over CM fields was also proved around the same time in work of Boxer, Caligari, G, and Piloni. And since then, there's also work of Allen, Carr, and Thorne that established actual automorphy for elliptic curves over, for certain elliptic curves over imaginary quadratic fields. Another application that we obtained is on the Ramanujan conjecture. So this bounds the absolute value of Fourier coefficients of modular eigenforms. This is something that was formulated maybe 100 years ago by Ramanujan for a particular modular form, and then was later on generalized to all modular forms known as the Ramanujan-Peterson conjecture, and then sort of reinterpreted in the setting of automorphic representations for, say, GLN. And then in that setting, it predicts that the local components of cuspidal automorphic representations of GLN are tempered. So temperedness means that the matrix coefficients of the representation are in L2 plus epsilon for every positive epsilon. So it's this kind of analytic condition. It's also sort of the tempered representations are the ones that are, in some sense, the building blocks for the category of irreducible admissible representations, in the sense that you can obtain all the others from tempered representations by some induction process, from tempered representations of smaller groups. So in 2018, again, in this large collaboration, we were able to show that if you start with a cuspidal automorphic representation of GL2 over a CM field, which has parallel weight 2, then it satisfies the generalized Ramanujan-Peterson conjecture. So the parallel weight 2 condition is saying that it has to contribute to the cohomology of the corresponding locally symmetric space with constant coefficients. So for instance, you can think about systems of Hecke eigenvalues that occur in the cohomology of arithmetic hyperbolic 3 manifolds with constant coefficients. And the theorem will apply to those. And the method for proving this theorem is exactly the same. You look at the associated Galois representation, you take all the symmetric powers of this Galois representation, and you establish a potential automorphy result for the symmetric powers. turns out that potential automorphy is good enough for getting the bound that you need towards Ramanujan. All right, and so the kind of the catalyst, the thing that led us to prove these two theorems was what was at the time ongoing work with Peter Schulze about the cohomology of Shimura varieties. So you can look at locally symmetric spaces for general groups, and usually these do not have an algebraic structure, and sometimes they do. And roughly when they do, you say that those locally symmetric spaces are really Shimura varieties. The Shimura varieties are really algebraic varieties defined over number fields. And they have a lot of symmetries. They have a Hecke symmetry, just like locally symmetric spaces do, but they also have a Galois symmetry that comes from the fact that they are defined over number fields. And so in many cases, they provide a geometric realization of the global Langlands correspondence because they have both kinds of symmetries. They're also higher dimensional generalizations of modular curves. So in joint work with Schulze, we looked at unitary Shimura varieties. And then there's sort of a folklore conjecture that predicts that the cohomology of a Shimura variety, the part of the cohomology that is concentrated outside the middle degree is somehow degenerate. And we proved a version of this conjecture for unitary Shimura varieties. So you want to look at a system of Hecke eigenvalues that occurs in the cohomology, either usual or with compact support. And if you assume that your system of Hecke eigenvalues is sufficiently generic, then you're able to show that the cohomology with compact support localized at the system of eigenvalues. So the part of the cohomology where you really see those eigenvalues is equal to 0 above the middle degree, above the degree given by the dimension of the Shimura variety. And then by Poincaré duality, you also get that the usual cohomology, when you localize at such a sufficiently generic system of Hecke eigenvalues, is concentrated only in the middle degree and above, and is equal to 0 below the middle degree. Right, so this is something that first we established this for compact Shimura varieties and then for non-compact Shimura varieties. And actually today, Teruhisa Koshikawa posted a paper on the archive where he gives an alternate approach to this theorem where he uses some of the geometric results that we established, but gives a different way to conclude in terms of cohomology. All right, so the proof of this theorem relies on the geometry of the Hodge-Tate period morphism, which really gives you a new way to think about the cohomology of Shimura varieties. So I don't want to get too technical, so I'll just say that the Hodge-Tate period morphism just is something that you have access to once you go to your Shimura variety with infinite level at P. There is a map from that Shimura variety, if you think about it as a perfectoid space, to a much simpler geometric object, which is a flag variety. And the idea is to compute the cohomology of a certain complex of sheaves on this flag variety instead of computing the cohomology of the Shimura variety directly. And so the key geometric ingredient in our work was to understand the fibers of the Hodge-Tate period morphism in terms of something called Igusa varieties, and which helped you really compute the cohomology of the fibers and understand this complex of sheaves on the flag variety. So I'll end here. I guess I just wanted to kind of give you some overview of what's been done, and there's some work in progress that kind of builds on this stuff, but let me just end here. Thank you very much.